So, so let us begin then. Okay. Uh, so last time I had a typing mistake on this slide, so I just wanted to mention that I have cleaned it up. Uh, Essentially, what we were saying last time that if I have a Hermitian matrix and I raise it to the power of n, then as n becomes larger and larger, this matrix starts approximating this A1 times A1 Hermitian. Just hold on. Hello? Hello? Yes? 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 Okay, so okay, so this is where I had a mistake last time. Um, uh, what this proof is showing is that because my lambda 1 is the largest eigenvalue, uh, and if I play this simple trick on this summation, I bring the lambda 1 raised to the power n outside, then what remains inside the summation, as n tends to infinity, it becomes 0. Because of this ratio, lambda m divided by lambda 1 is always going to be less than 1. And so that is the proof of this property. And we have seen that this property has actually many applications. Frozen. We saw several applications of this property last time. Okay. So that was just a quick recap of one place where I had a little bit of an issue in the last lecture session. So moving right along, we are now going to talk about some advanced signal processing techniques that allow us to improve upon the performance of the frequency of arrival estimation problem. Okay, so we have seen that we can estimate the frequencies of incoming signals in a composite of signals by performing essentially by passing the signal through a discrete Fourier transform processor. And we would take the output of the DFT, which can be thought of as a bank of finite impulse response filters of certain specific length n, and then we would just take the average power coming out of that bank of DFT filters. And then as a result, what we get is what we have seen earlier is an estimate of the power spectral density of the incoming signal. And when the incoming signal has multiple narrowband signals, this power spectral density actually looks like the sequence of delta functions with some noise floor, some white noise floor. That is one of the diagrams that we had seen earlier. Now, our estimator, in order for us to be so that we can estimate these frequencies well, our estimator should be like a needle. It should actually sharply point us to the locations of the peaks in the power spectral density estimation. It should be sharp and it should be pointed to the actual frequency. But instead of that, what we have seen is that our PSD-based estimator is more like our finger. It is a little bit spread out at the top. It is not like a sharp needle. Unless if the incoming frequencies happen to fall on an exact multiple of 1 over n. If they fall on a multiple of 1 over n, then our power spectral density based estimator does a very good job. In fact, although we are not going to do that, it can be proven that this DFT based estimator of FOA is the optimal estimator, provided that incoming frequencies are truly cyclical. But this we saw right on at the very first lecture, that as soon as we discretize the time, we don't have a guarantee that our incoming signal will be cyclical. It may be aperiodic. Only when its frequency is an integer multiple of 1 over n, then only it is really a truly periodic signal. And so in that case, our DFT based estimator becomes smeary. It has kind of low resolution given a specific value of n. And because of that, if there are multiple signals whose frequencies are kind of close together, then they get fused. And even if a signal which is far apart, even if we consider two signals which are far apart in the frequency domain, that those signals may also experience a problem, especially if one of the two signals is weaker compared to the other. It may get kind of buried under the side lobes of the DFT sync shape response, the magnitude response. And so those side lobes can be thought of as like multiple smaller fingers of this main finger. So what we want is really an estimator which does not exhibit this property. It is first of all sharper, and secondly it doesn't have the side lobes. Its main lobe should be sharper, and its side lobes should be much suppressed. And so we are going to talk about 3 signal processing techniques that attempt to achieve our desired performance of the FOA estimator and remove some of these deficiencies of this power spectral density based estimation. And they work even when the incoming frequencies are not multiples of 1 over n. And so these 3 techniques that we are going to look at, one is the music algorithm that we have seen last time. The other is called MVDR algorithm. The third is called the expectation maximization algorithm. And there we may be taking a compressive sensing viewpoint to this problem. Now, what I want to emphasize to you is that although these three algorithms are getting applied to the FOA estimation problem here, these are very powerful algorithms. These are techniques which actually have underlying mathematics and calculus and linear algebra, which is more general than just the specific application that we are considering. And their application is not restricted to just this particular problem statement. They are widely applicable, and actually they are currently being researched across the research community in the research community across the world. So I wish to emphasize that these are some of the very powerful techniques and some very nice methodologies that we can benefit from. Okay. Let us move forward. So we have seen the eigen analysis based algorithm, which is this music algorithm earlier, and there we actually leverage one of the properties of the eigen vector decomposition that we have mentioned earlier. Essentially, what we are doing is we are finding out the noise subspace of incoming signal, and that subspace will have exactly the number of dimensions that equal n minus k, where k is the number of simultaneous transmitters. And then first we determine the number of sources, and then what we say is that we will actually form what is known as the pseudo spectrum. The reason it's called pseudo spectrum is because this is really not the this does not comply with the mathematical definition of power spectral density. If you take the inverse Fourier transform of the pseudo spectrum, you do not get autocorrelation sequence. But still it is pseudo power spectrum because it is computed as a function of the small f, where f varies from minus 0.5 to 0.5. And what we do is for each f, we calculate our vector Wn of f, which we have defined earlier. And then we calculate this ratio, which is shown here, where V is a matrix that forms the basis of the noise subspace. Basically, the column vectors of matrix capital V are the eigenvectors corresponding to the noise subspace of the incoming signal. And this we determine by determining this matrix V we form by determining the eigenvectors corresponding to the smallest eigenvalue of this matrix RSX. And so this expression here can also be written alternatively in this manner. I think this is probably one of the exercises that I had asked you to do in the ongoing lab. Okay, so I'll take a moment here and maybe let me see if I can use one of the features of this. Okay. Why is the music pseudo spectrum guaranteed to exhibit allows spike at the location coming signal system. Okay, so I have asked this question. In case if you want to answer, you can just put it here. This is like um, kind of a little bit of a slow way to do this. Um, by the way, do you see this question that I have posted here on the poll window? In fact, I'll ask you to speak out if you know the answer of this question. Why is this spectrum, pseudo spectrum, uh, expected to give us a nice sharp impulse at the location of the correct value of f? Anyone? Amishi, what do you think? Are you there, Nemishi? Nemishi, you will have to unmute yourself if you are there. Do you know why this pseudo spectrum will be giving a very high value at the correct frequency location? Yes, no? Unmuted yourself.
Hello.
Yeah. So did you understand the question?
Yes, sir. Sir, I don't get the answer.
You don't understand? Okay. Kishan, what do you think? Kishan, are you there?
Hello,
Yes.
sir. Am I audible?
Yeah, I can hear you.
Yeah, sir. At that frequency, like when that frequency comes, the denominator becomes zero because
Right.
of
Yeah. Why does the denominator
orthogonality.
become zero?
Because the columns, like the multiplication, will be zero because they are orthogonal to the frequency. Like the columns are.
Right. So this is the property 5b that we have seen earlier, that each of these column vectors a of n up to a of n minus a plus 1, because they belong to the noise subspace, they are perpendicular to the signal subspace. And then the signal subspace is actually the subspace of this n-dimensional space where the signals are present. And so that entire subspace, any vector in that subspace is guaranteed to be 90 degree from each one of the columns V of I. And so obviously when we consider a vector corresponding to the correct frequency, that vector is going to be 90 degree for each of V of I, and so we get this dot product to be 0. 1 divided by 0 is infinity, and so at the correct location of the frequency we get a very large number. It won't be infinity because it won't be 1 divided by 0 necessarily because of some noise that will be present, but it should still be pretty large. Okay, so that is what this particular slide says. Okay, now let us summarize this algorithm that we had seen last time. Essentially, what we will be doing is using the n samples of incoming signal, we will estimate the signal correlation matrix RXF. So there is a typo here, we will correct it next time. And then we will perform the eigenvalue decomposition of that correlation matrix. We will determine a cluster formed by the smallest kappa eigenvalues, where we know that kappa has to be necessarily equal to n minus k, because capital K is the number of active transmitters, and so the remaining eigenvalues all should be equal to the noise. And so from that we will be able to determine the number of active sources K as n minus kappa. Then we will collect the eigenvectors corresponding to those smallest eigenvalues, which we have corresponded to the variance of the noise. We will form this matrix capital V using those eigenvectors. Okay. Then we will actually sample this frequency axis from minus 0.5 to positive 0.5 in a large number of samples, maybe 1,000 or so. And then for each value of small f within this range, we will calculate this pseudo spectrum using this Hermitian dot product. And then that will give us our pseudo spectrum whose highest peak will indicate to us the location of the frequency of arrival. So this is the music algorithm that I will ask you to simulate in the next upcoming lab. Okay, now I'm going to get to another technique which is called minimum variance distortionless response method. So the music algorithm is purely linear algebra. There is just nothing else than linear algebra. We just do eigen decomposition, and provided that we have fully understood the properties of EVD, then that is all we need to know to understand the music algorithm. On the other hand, this MVDR is now going to ask us to get into the calculus, specifically differentiation, derivatives, gradients, etc. So now we are kind of jumping onto some other branch of mathematics. But the algorithm's concept is kind of also, it goes to some extent from linear algebra also. Actually, one of the properties of correlation matrices that we had seen earlier. So the objective of the MVDR is to say that we don't want to restrict ourselves to Wn of f. Remember, Wn of f is this complex exponential filter. It's n samples make up the samples of complex exponential at frequency small f. But we have seen that this, if we restrict ourselves to Wn of f only, then we'll get into these problems of low resolution smearing, leakage, etc. So if we want to do better than that, then we have to say that we will not restrict our filter to have necessarily the same coefficients that define the DFT based filter bank. Our filter will still be based on a bank of filters, but the coefficients will not be Wn of f. Although we would like it to exhibit the properties of this Wn of f, meaning it should be matched to the incoming signal frequency, but at the same time, we want it to suppress the side lobes as much as possible. And we want it to narrow down the main lobe also as much as possible. And so the mathematical statement of the problem is that in order to suppress the side lobes and in order to narrow down the main lobe, we want this filter to exhibit zero output. It should not register any energy whatsoever, which is to say that expected value of the magnitude squared of the filter output should be zero. Okay, basically the filter should reject everything that is incoming to the filter. Except we want to say that obviously we don't want to blank out the actual incoming signal while doing that. We don't want our filter to kind of overdo its required task of rejecting all the unwanted frequencies. So we will put a constraint saying that if the incoming signal matches with this frequency f of our interest, then we would like the filter to produce a strong output. But otherwise, as soon as the incoming signal frequency deviates from f, we want the filter to register basically zero output or as small as possible output in terms of magnitude squared. So the statement of the problem is that we want to minimize the magnitude squared of the filter output. If we cannot make it zero, we will still try to make it as small as mathematically possible, except that if the filter input x of n is itself a certain frequency exponential that we are designing this filter for, then we want the filter to give us a strong output, which is 1. So the statement of the optimization problem is that if the incoming signal frequency is certain frequency f, then the output should be 1. As soon as it becomes any frequency different from f, the filter output should be 0 or as small as possible. Now remember that we have previously formulated expected value of magnitude squared of the filter output as Wn Hermitian Rxx Wn, where W is the vector of filter coefficient of length n. Now this one here is actually this should ring a bell. We have considered this in one of the properties of the correlation matrix R. So who can tell me what did we do? Let me again ask someone. So Radhika, can you tell me what this Wn Hermitian Rxx Wn represents, or how to think about this term? Radhika, are you there? Joel, what do you think? We have talked about this term in the previous lecture only. Joel?
So,
Yeah, go ahead.
are you able to hear me?
Yes, yes.
Sir, I think, sir, this we said that this will be always greater than equal to 0, this entire term.
Yeah, that is correct. But more recently, we have considered one property of correlation matrix where we equated this to certain value, and from that we derived some geometrical interpretation of this quantity. Do you recall that? Yes, no?
No, sir.
So, Bhavesh, what do you think? Bhavesh, are you there? Do you understand my question, Bhavesh? No? Bhavesh, yes, no? What do you think? Go ahead. The Bhavesh is silent. Arushi, what do you think, Arushi? Yes, go ahead, Arushi. Did you understand the question?
Sir, am I audible now?
Yeah, yeah. I can hear you.
Sir, this will be ellipse.
Yes, yes. Correct.
Yes, sir.
So Joel, Bhavesh, Radhika, looks like you probably were not paying attention last time. We considered that when we equate this expression to a constant, we get an elliptical contour. This was one of the properties that we had seen last time. Bhavesh, do you recall that? I don't know where is Bhavesh, maybe he's not there right now. Okay, fine, we will move on. Okay, so the statement of the problem is that we want to minimize this quadratic term. Actually, we said that this term, if we equate it to a constant, defines a quadratic equation. And we want to minimize this quadratic term because it is the expected value of the filter output magnitude squared under the constraint that the filter coefficient vector dot product with this specific frequency should be 1. Okay, so that is the statement of the problem. And remember, as Arushi said, this expression here, which we are trying to minimize, can be visualized as ellipses. As we try to reduce this quantity, the major axis and the minor axis, essentially the radius of this ellipse reduces. So if we are at the outermost ellipse, then maybe we have not minimized this term as much. If we can bring it down to the smaller and smaller ellipses, we are minimizing it. But remember, the smallest value of this ellipse is just a dot. It's an ellipse with major axes and minor axes which are all 0. Which means that the filter output is 0 essentially. But such a filter is not a useful filter. It basically just blanks out everything. Then we actually don't need even a filter. We just multiply the incoming signal by 0 and that will do that job. What we want is a filter which actually satisfies this constraint, that the inner product of W filter coefficient with WF of n, the frequency for which we are designing the filter, is unity. And now, just like this equation can be considered as quadratic equation whose geometrical representation is in the form of an ellipse, this equation here can be thought of as a line because it's all there are no power terms here, there are no exponential terms. The unknowns, which are the coefficients of W's, get multiplied by the known coefficients which are coming from Wn of f, and then the product is equal to 1. So you can think of this forming a line in multidimensional space, or actually a plane. In 2 dimensions, this will form a line. In 3 dimensions, this equation will form a plane. And then in higher dimensions, it will form what is known as a hyperplane. So basically, it's a linear equation. And what we want is that we want to keep on reducing this oval until they touch this hyperplane. Okay, so if we are at the outermost oval, then we know we can do better. If we are at the middle oval, then maybe we have already reached the optimal point. Because if we try to reduce the oval further, then we will not be meeting our constraint. We will not be at a point on the line. So if we either touch this line in 2 points, or in general in multidimensional space, if this hyperplane crosses this oval or this ellipse in multiple points, it means that this term has still not been minimized. If the hyperplane doesn't even meet this ellipse, then it means that we have reduced this term maybe way too much, such that we are not anymore satisfying this constraint. So when we actually satisfy the constraint, we want this line to be a tangent to this ellipse, because it is at that point that we are along this line, as well as we have minimized this quadratic equation as much as we could. The other way to say that is that the tangents or the derivatives or the gradients in this multidimensional space of both these functions, this quadratic function and the linear function, they should become parallel at the point which we are trying to optimize and we are trying to derive. So in our simple visualization, all that we are saying is that if I draw the tangent to this ellipse, I want to eventually reach a point on the ellipse for which the drawn tangent is parallel to the line. When that happens, something like what is shown in this diagram is happening, and this diagram should have convinced you that this point here that I'm touching here is the optimal solution point. Now, the way to state that mathematically is that the gradient of this quadratic term and the gradient of this line, they should become parallel, except maybe there is some scalar multiplier that we have denoted by lambda. The effect of this scalar multiplier is only to just scale the one equation with respect to other. It doesn't change the parallel nature of the tangents to both of these geometric shapes. And so that is the statement of the Lagrange multiplier problem. We want to take the derivative of this and the derivative of this quadratic term and the derivative of this linear term, and we want to equate them both. Except that before we put an equality sign, we allow this Lagrange multiplier to scale one of the two gradients so that the equality becomes mathematically exact. Okay, so that is how we are solving this constraint optimization problem. Now, one thing that I want to mention is that when we take this gradient, because of this individual coefficients having complex valued nature, for some reason we have to take complex conjugate. We have to take the derivative with respect to the complex conjugate of the variable that we are trying to determine. The reason why we have to take complex conjugate is a little bit detailed. I will not get into that, but I'll give you a supplementary material that you can read on later offline. Okay, and then the other thing is that I'm going to now state this problem in so that the math becomes little simpler just from the notational perspective. Essentially, I'm going to replace this Wn filter vector with Z, and this Rxx I'm going to just call it R. So the problem is that we want to minimize this Z Hermitian Rz subject to the constraint that Z Hermitian A is equal to 1, where A is this Wn of F. Okay, and we have seen that the solution is the point, or actually in this multidimensional space, this vector Z, for which this linear term, now the tangent to the linear term is that linear equation itself. The tangent of a line is the line itself. So we want the tangent to this elliptical term to be parallel to this line. Okay, so that is our insight that we got from doing this type of diagram. Now, just like I kind of glossed over why we have to take this when we calculate the tangent. Essentially, we have to take gradient operation. Why we have to take the gradient with respect to the complex conjugate of the variable that we are trying to determine. That is one thing that I am not saying. The other thing that I am going to gloss over is that this is getting into the calculus of complex variables, and not only complex variables. We are talking about calculus of vector valued complex variables. We are trying to take the derivatives with respect to a vector now, because it is this vector Z that we are trying to determine. Methodology is still the same. If you want to determine the minimum or maximum point of a function, we take the derivative of that function and set it to 0. So that basic methodology that we have learned in the high school is still the same, except the derivatives are happening with respect to a vector. And furthermore, the elements of this vector are complex values. And so there are a lot of questions that we are leaving unanswered. First of all, what is meant by taking the derivative of a complex number with respect to another complex number? We can understand what is meant by derivative of a real number with respect to another real function. So the derivative with respect to complex numbers we haven't talked about at all. how can we take derivative of some scalar term, for example, this Z Hermitian RZ, which is a scalar, how can we take its derivative with respect to a vector? That also is something that we have not talked about. All that I'm giving you is this table. It's almost as if I'm telling you that just memorize this table. This table is very useful. It allows you to solve many such problems of complex variable optimization. But how do we get the elements, the entries of this table? Because again, I'm not specifying. So there is a lot of concepts of complex variable calculus that I am not getting into. As I said, I will give you a supplementary material to read later today. But for our purpose, we will just take this to be the case. And then essentially, we are going to solve the statement of the problem that we have earlier stated. We are going to define this function Q of R, which is a function of Z and lambda. These are the two unknowns that we are trying to determine. And the entire function is given like this. So this function here is actually same as what we said earlier. This equality, except that I brought the right hand side of this equality on the other side, and then I am setting the derivative of that resultant function to 0. That is all that I am doing. So the methodology here is very familiar to you. It's a standard way of determining the optimal solution of any real valued function. But here we are considering this vector valued operation. We are taking this quantity, remember this is a scalar quantity. As a function of Z, it traces out ovals or ellipses, the first term, and the second term traces out a hyperplane. But for a given value of Z and lambda, it's just a scalar. And so I'm going to take its derivative with respect to Z conjugate, as we said earlier on, and I'm going to set it to 0. If I take derivative of this Q function with respect to Z conjugate, it turns out to be RZ minus lambda A. How did it turn out to be that? I just used this table here. If I take derivative of Z Hermitian A with respect to Z conjugate, I just get A. If I take derivative of Z Hermitian AZ, then I get AZ. Using the second row of the table, I got this equation, which I'm setting to 0, and so I get Z is equal to lambda times R inverse A. Okay, now all that we need to do now is determine the value of lambda, and so I'm going to take derivative of that Q function with respect to lambda. I will set it to 0, and when I do that, here one thing that I'm going to do is I'm going to substitute the formulation of Z that I got here. Z, I have already determined it to be like this, and so this Z Hermitian becomes lambda A Hermitian R inverse, and that when I set it to 0, I get the value of lambda. And so the final solution I get by substituting this value of lambda in this equation. So if I substitute lambda is equal to A Hermitian R inverse A that I got in equation 5, finally I get the solution that I am looking for. Okay, so there is a lot of calculus here, some math concepts that we have glossed over, but the stepwise procedure is something that I think you should familiarize yourself with. because this is a very powerful technique, this Lagrange technique. The concept is given by this visual diagram, and its stepwise process is listed out here. It just uses some 2 or 3 steps. If you know the rules of differentiation, and this doesn't have to be a complex valued case all the time. It doesn't have to involve vectors all the time. So in many cases, it is just standard derivative rules that you have studied in your high school calculus course. Then actually you can still apply the exact same problem solution technique, the step 0, 1, and 2, and you get the optimal answer. In our case, our optimal answer becomes like this. Okay, so now let us see if we plug in our original notation in this solution that we got. R inverse becomes Rx inverse. A becomes the vector of complex exponential, and therefore our final solution regarding the filter coefficient vector becomes this. Now here again, this denominator is a scalar, as you have seen, and so we can define it to be some scalar beta that will be given like this. So our filter has become our original DFT filter, Wn of f, except that we are multiplying it by the inverse of the correlation matrix of the incoming signal. And the result we are multiplying with this scalar beta. So that is the summary of the MVDR technique. Okay, so I'm going to actually stop, take a break at this time, and then we'll come back after 2 minutes.